It's one of the most dangerous, ambitious, and borderline insane ideas in modern science. Drill directly into the heart of an active volcano. Not metaphorically, not from a safe distance, but literally lower a drill thousands of feet into the earth until it pierces the roof of a magma chamber. A team of scientists in Iceland is doing exactly that. These researchers are aiming for what's never been done before, getting up close and personal with molten rock, bubbling just beneath the Earth's surface. And they aren't doing this for the thrill. They believe that within this fiery furnace lies the key to revolutionizing the future of energy. But before we celebrate any scientific breakthroughs, we need to ask, are they playing with fire, literally? Could this risky move trigger a volcanic eruption that endangers lives, or even the planet's climate? And why Iceland, of all places? What makes this island nation the perfect site for one of the boldest geologic experiments in history? Welcome to a place where nature rumbles under your feet, and the landscape is shaped not just by time, but by explosive force. This is Iceland, a country of fire and ice, of glaciers and lava fields, of beauty and danger intricately entwined. And at the center of this scientific story lies the Iceland Deep Drilling Project, an extraordinary attempt to go deeper than anyone ever has into the bowels of the Earth. No one has ever drilled directly into an active magma chamber and lived to study it. But now, thanks to years of planning, technology, and just enough daring, that's about to change. The project begins in earnest at a location called Krafla, a brooding volcano in northeastern Iceland that last erupted in the 1980s. Scientists have chosen this very site to make history. But to understand why drilling into magma could be so scientifically important, we need to explore what makes Iceland such a geological wonderland in the first place. From a distance, the island might look like a quiet, frozen paradise. But underneath lies one of the most geologically active zones on Earth. Iceland is perched directly atop the mid-Atlantic ridge, where two massive tectonic plates, the North American and Eurasian plates, are constantly moving apart. As they spread, magma from deep inside the Earth rises to fill the gap, pushing up new crust and creating new land. It's like watching the Earth breathe in slow motion. And sometimes those breaths come with fire. In fact, Iceland is one of the few places on Earth where you can actually see this tectonic process happening on land. Walk through the Thingvellir Rift Valley and you're literally stepping between continents. The Earth is splitting apart, centimeter by centimeter, and magma is never far below. That's why this island has an unusually high number of hot springs, geysers, and of course volcanoes. Even in the middle of winter, Icelanders can soak in warm, natural pools heated by geothermal energy. It's not just scenic, it's powerful. And that power is exactly what these scientists are trying to tap into. The volcano they've chosen for their bold experiment, Krafla, has quite the explosive history. Between 1975 and 1984, Krafla erupted 9 times. That's not a typo, 9 separate eruptions in less than a decade. It became one of the most studied volcanoes on the planet. Thanks to this frequent activity, geologists were able to use seismic data to map out the magma chamber lurking below the caldera. By analyzing the way earthquake waves moved through the ground, they could triangulate where the molten rock was hiding. The answer? About 1.2 miles beneath the surface. Deep but not unreachable. And that's where things get truly exciting. Until now, geothermal plants near Krafla have drilled dozens of boreholes to tap into the underground heat. But none of them ever reached the actual magma. Most stopped hundreds of meters above the chamber. Why? Because magma isn't something you mess around with. Get too close and you risk triggering an eruption. But the scientists involved in the Iceland Deep Drilling Project believe they've found a way to safely reach it. And if they succeed, the results could change everything we know about geothermal energy. But to appreciate what they're doing now, we have to rewind to 2008. That year, a company called Landsvirkjun, the national power company of Iceland, began drilling at Krafla with the intention of reaching 4,000 meters deep. That's over 13,000 feet. But they never made it that far. At around 2,100 meters, or roughly 6,800 feet, something strange happened. The drill suddenly dropped, fast. Nearly 100 meters in seconds. Then it stopped cold. When they pulled it up, it was stuck. They'd hit something unexpected, obsidian. A hard, glassy volcanic rock that forms when lava cools rapidly. It wasn't supposed to be there. That's when they realized what had happened. They had accidentally pierced the roof of the magma chamber. Molten rock had surged into the borehole and solidified around the drill, effectively sealing it shut with volcanic glass. It was an accidental, unrepeatable success. But it also proved that magma could, in fact, be reached. This accidental breakthrough laid the foundation for what's happening now. The team, better equipped and more prepared, is returning to Krafla with a plan to do it deliberately, and this time safely. But how do you drill into something that melts anything that touches it? That's where science gets creative. The idea is to slowly cool the area directly in front of the drill by injecting cold water, allowing the magma to solidify just enough to form a protective layer. Imagine forming a glassy sock of volcanic rock that shields the drill bit from direct contact with the molten core. It's risky, but if it works, it could open a window into the most extreme environment humans have ever studied directly. Still, the stakes couldn't be higher. One of the main concerns is triggering an unintended eruption. As magma rises to the surface, the pressure drops. This allows gases dissolved in the molten rock, like water vapor, carbon dioxide, and sulfur dioxide, to rapidly expand. Think of it like shaking a soda bottle and popping the cap. The pressure change can cause the magma to fragment into tiny particles, ash, which then mixes with hot gases and shoots high into the sky. Beautiful. Absolutely. But also deadly. Ash clouds can drift for thousands of miles, clog airplane engines, and cause massive disruptions to air travel and global commerce. The world got a reminder of that danger in 2010, when another Icelandic volcano, Eyjafjallajökull, erupted. Its ash cloud grounded thousands of flights across Europe for nearly a week, costing airlines billions and leaving passengers stranded. At the time, it was a stark lesson in how one relatively small eruption could bring international airspace to a standstill. And it's not just about travel. Ash clouds can change global climate patterns. When large amounts of ash and sulfur dioxide are released into the atmosphere, they can reflect sunlight back into space, causing temporary cooling. The 1815 eruption of Mount Tambora in Indonesia triggered what became known as the Year Without a Summer, a time of crop failures and food shortages across the northern hemisphere. Scientists studying these effects believe that ancient supereruptions may have caused mass extinction events. So yes, drilling into a magma chamber carries enormous risk. One wrong move and the Earth could respond with fire and ash. But the potential benefits are just as extraordinary. If we can safely tap into the energy of magma, it could provide virtually unlimited geothermal power. Unlike fossil fuels, geothermal energy is clean, renewable, and always available, no matter the weather. And magma is the ultimate heat source. Traditional geothermal wells extract heat from underground water reservoirs that are heated by nearby magma. But if you can drill directly into the magma itself, the energy output could be 5 to 10 times greater. It would be a game changer for nations trying to transition away from oil and gas. What's more, by studying the magma up close, scientists hope to gain insight into volcanic behavior, potentially improving eruption forecasts and saving lives. Right now, predicting volcanic eruptions is still more art than science. But with real-time data from inside a magma chamber, its pressure, temperature, gas composition, researchers might finally understand what signals precede an explosion. That knowledge could benefit every country with active volcanoes, from Japan to Indonesia to the United States. But for now, all eyes are on Iceland. The drilling has begun, or soon will, and with it comes a sense of awe, fear, and wonder. Will they find what they're looking for? Will the Earth cooperate? Or will it remind us that beneath our feet lies a force far more powerful than any machine? The answers are coming and they're buried in fire. Wiped out. That's what happened the last time a geologic catastrophe reshaped the planet. 90% of all marine life and 70% of land animals vanished in what scientists now call the Great Dying, some 252 million years ago. It was the most severe mass extinction in Earth's history, and it was likely triggered by massive volcanic eruptions. That dark legacy looms like a shadow over any attempt to meddle with magma. But returning to the present day, the scientists working at Krafla volcano in Iceland believe they're in a far safer and more stable situation. The magma beneath Krafla is thought to be older, with far fewer dissolved gases. And that simple detail changes everything. It dramatically lowers the chances of explosive eruptions and minimizes the risk of vast ash clouds being released into the sky. That makes this drilling project not only fascinating but also relatively safe, and perhaps even predictable. Still, relatively safe is not the same as without risk. There's always a chance, however small, that nature could push back. So the question stands, why would anyone take this chance and drill directly into a volcano? Because now we understand something remarkable about Iceland. Something that transforms this project from a scientific curiosity into a global opportunity. Beneath this nation's dramatic landscapes lies a vast ocean of untapped potential. The very magma that fuels its volcanoes is a gateway to a new energy frontier. It radiates intense heat, and that heat could, in principle, supply clean, abundant, and nearly limitless power to the entire country, and perhaps even beyond. Icelanders already know how to make geothermal energy work for them. The country has a long tradition of harnessing the Earth's internal warmth, using it to produce electricity and heat homes. But what's being done now could elevate geothermal energy to a whole new level. It could reshape how the world powers its future. Let's take a moment to break it down. Traditional geothermal energy systems work by tapping into pockets of hot water and steam that are trapped deep underground in porous rock layers. These systems often require drilling several kilometers into the earth. Once the steam reaches the surface, it's channeled into turbines to generate electricity. The beauty of this approach is in its stability. Unlike solar or wind, which depend on unpredictable weather patterns, geothermal energy is always available. It doesn't matter if the sun's out or the wind's blowing, it's always the same temperature underground. And that makes geothermal power an incredibly reliable form of renewable energy. But researchers now believe there's a way to supercharge this entire process. Enter the concept of supercritical geothermal energy. This next-generation technique taps into an even hotter and more powerful state of matter, supercritical water. When water is exposed to extreme temperatures and pressures, conditions typically found near magma chambers, it enters this bizarre in-between state. It's not quite a gas and not quite a liquid. It's both at once. And that makes it incredibly efficient at storing and transferring heat. Imagine the energy potential of steam, but multiplied many times over. Supercritical water can reach temperatures of 450 degrees Celsius, or over 840 degrees Fahrenheit. At those levels, it becomes an absolute powerhouse for generating energy. Just one well drilled into a supercritical reservoir could produce 5 to 10 times more electricity than a conventional geothermal well. It's a stunning leap forward in efficiency, and one that could radically reduce the number of wells needed to power entire cities. Fewer wells mean smaller environmental footprints and lower infrastructure costs. But of course, to reach these supercritical zones, we need to drill deeper. Much deeper. And closer to magma than ever before. This is what makes the Krafla project so daring, and so full of promise. The magma chamber beneath Krafla is essentially a natural pressure cooker. If scientists can manage to drill safely into it and extract energy from the surrounding superheated fluids, they'll unlock one of the most potent renewable resources on Earth. But it's not just about power, it's about possibility. It's about transforming our entire approach to how we fuel human civilization. Let's bring things back to the surface for a moment. If you've ever visited Iceland, you've probably heard of the Blue Lagoon. It's one of the country's most iconic destinations, a stunning, man-made geothermal spa filled with milky blue, mineral-rich water. But what most people don't know is that it wouldn't exist without geothermal power. The lagoon is actually a byproduct of the Svartsengi power plant. Hot wastewater from geothermal electricity production is channeled into the lagoon, where it cools and forms a luxurious, naturally heated pool. The water is packed with silica, microalgae, and minerals known for their health benefits. It's a living symbol of how Iceland has learned to live in harmony with its volcanic heart. Now, imagine this. A single geothermal well at Svartsengi might generate about 5 megawatts of electricity. That's enough to power roughly 5,000 homes. But a supercritical geothermal well, of the kind scientists are now trying to develop, could produce 50 megawatts or more, enough for 50,000 homes from a single borehole. That's a tenfold increase in power output. And this kind of efficiency changes the math. If geothermal energy can become that powerful, it could finally step into the global spotlight as a major contender alongside wind, solar, and even nuclear. What's even more encouraging is the human side of this transition. Many of the skills needed to drill these super deep wells are already widespread in the oil and gas industry. The same workers who once drilled for fossil fuels could be retrained to work on geothermal projects. That means the shift to clean energy doesn't have to leave people behind. Instead, it offers a pathway to re-employment and economic renewal, especially in regions that have long depended on carbon-intensive industries. Geothermal energy, powered by magma, isn't just an environmental solution. It's a human one. But before we get carried away, we have to ask, if this is such a promising source of energy, why aren't we drilling into every known magma chamber already? The truth is, it's not that simple. Drilling into magma presents a formidable set of technical and financial challenges. First and foremost, the temperatures involved are extreme. Equipment designed for standard geothermal conditions simply can't survive the 1,000-degree heat near a magma body. At those temperatures, metal softens, electronics fail, and drilling fluids vaporize. Creating machinery that can operate reliably in that environment requires innovative engineering and a lot of investment. Then there's the issue of pressure. The deeper you go, the more intense the forces become. Combine that with unpredictable rock formations, pockets of volatile gas, and the ever-present risk of hitting molten rock, and you've got one of the most complex drilling operations imaginable. These aren't just engineering problems, they're financial ones. Building and deploying the necessary equipment is expensive. Running the test, monitoring for safety, containing and managing the extreme heat and pressure. All of it adds up. And until these technologies become more affordable and scalable, supercritical geothermal energy will remain on the cutting edge rather than the mainstream. But the Iceland Deep Drilling Project is changing that. It's not just a science experiment, it's a proving ground for the technologies of tomorrow. Every sensor they install, every meter they drill, every data point they collect. It all adds to our understanding of how to tap into the Earth's deepest, hottest, most powerful forces safely. These scientists aren't just chasing curiosity. They're carving a path toward an energy revolution. They're not just digging a hole into a volcano. They're digging into the future itself. When they finally reach the magma, and they will, it won't just be a moment of scientific triumph. It'll be a turning point in our relationship with the Earth. For centuries, we've feared volcanoes, seeing them as destroyers, as signs of nature's fury. But now, for perhaps the first time in history, we're learning how to work with them. To channel their energy. To harness their heat. And to do it not for conquest but for coexistence. This upcoming drill at Krafla is more than just a milestone. It's a glimpse of what's possible when we blend courage with caution, ambition with responsibility. Yes, there are risks, but the potential rewards are staggering. Cleaner air. Safer energy. A world less dependent on fossil fuels. A world more in balance with the forces that shape it. And it doesn't end in Iceland. Around the world, other nations are taking notice. In China, scientists have launched an effort to drill one of the deepest holes ever attempted. Is it also about geothermal energy? Or are they searching for something even deeper, even older? What will they find as they push the limits of human exploration? That question is waiting for us just below the surface. So as we stand at the edge of a volcano and listen to the quiet rumble beneath our feet, we are reminded of something profound. The Earth is alive. It moves. It breathes. It burns. And now, finally, we are learning how to listen.